UMass. We're an RSO, and we are having our recruitment like this week and next week. I know this is kind of late, but we have our first one tonight. It's just a panel and like some open networking afterwards. And then there's Jeopardy tomorrow, and then there's another event on Monday. Basically what we do is we're just kind of like a tight-knit community of people that are interested in tech, so like all majors are welcome. I know you guys are welcome, but all majors are welcome, and it's kind of a great community to kind of talk about our interests in tech and also like to make friends in classes and things like that, and also professional development, like mock interviews, resume. Oh, if you guys
you should write the time and place also. You
look at it.
You can write over on that
Oh,
board.
it's gonna be an ILC, but we're posting like the exact location here. Don't look it up right now because I know phones are not.
Yeah. Okay. Yeah, you can write that up. All right. Hello everyone. Hello everyone. Computers away and all that jazz. First thing first. This was bothering me quite a lot, but I ended up finding a counterexample. Here's a counterexample. It turns out, by the way, finding a counterexample for this is for everyone who might not have caught it or doesn't remember. This is for the scheduling problem with greedy heuristics. This is a counterexample to the minimum overlap example. And you can see that it forces you to pick this middle one because it has the fewest overlaps out of any of them. And then this one breaks the optimal solution, which is all 4 of these in a row. Cool? Great. Yay. Turns out it is very hard to find a counterexample, so I don't blame all of you guys for not finding it. It took me a while to figure it out. Okay. One more administrative thing. Sort of officially now, the coding section of Project 2 has been released. We have an initial autograder, but we haven't uploaded it to Gradescope yet because we want to test it and all of that. Plus, you guys don't need an autograder, just make it work and test it yourself, right? We'll release that somewhat soon. Yeah, I will say, I don't know, how many people have like completed the coding section? Who did it over break or something? Okay, that's fair enough, fair enough. Who started the coding section? Okay, probably smart, I'll be honest. The coding section I think will take a little while. A lot of people, I would say a lot of people are going to run into problems with runtime. So you should probably start a little bit early just so you can work through it. I also really recommend strongly that you don't do, definitely don't do Ford Fulkerson because it could really be really slow. Admin carp can also be very slow. Doing something like the other algorithms we learned will make it much more tractable. Tractable means like feasible, by the way. Cool, that's a counterexample. Yeah. All right, any questions on Project 2, by the way? Okay, I've reopened the written section. Oh, one more thing, I guess, actually. I went through the initial submissions for the written, and I was somewhat perturbed, I'll say, by the amount of obviously AI submissions. So I decided to go through and mark them and give partial credit if it seems like there was AI used, and 0 credit if I think it was entirely an AI submission. If you think that I erroneously marked you, then you can tell me about it. That's only going to be 10% of the written portion, and I'm not opposed to you guys all using AI tools to help. But when I see the submissions that are pretty obviously copy and pasted from AI, including breaking the formatting and LaTeX, I'm just going to say that you didn't submit it because that takes about 10 seconds. And the point of this is to get first started on the problem. Because now if you haven't started the problem yet, to those of you who may have not done that, you're going to have a really hard time in the next week, I'll be honest. So anyway, that's that. You can check, yeah.
Do we need to write out our,
Not if you're using an off-the-shelf one. If you're modifying any of them, then you do need to. Yeah, and you can just describe the modifications for the most part. If it is a lot of modifications, though, then you should probably write your own algorithm. Cool. Any other questions? Okay, cool. So today we are going to, I guess we'll first review greedy. Can someone tell me? Can someone describe to me what a greedy algorithm is? Yeah. Exactly. So it is an algorithm that only looks at global, or not global, local information, and then just recursively makes some sort of heuristic decision, and that leads to an optimal solution. So the example that we did in class previously was we had a whole bunch of different paintings. I chose something very hard to draw, I guess. I had a whole bunch of paintings that had different values, and we said that we wanted to go through and steal as much value as we could, and we only were able to take some number of paintings. So how do we do this? If we don't know how many paintings we're able to take, we just know if we fill up our bag. Well, the obvious thing to do is just take the most valuable one first and work our way down. It's a very trivial example of a greedy algorithm. Where it is a little bit trickier is proving that it's correct and proving its runtime. The runtime is actually fairly easy, but proving correctness for greedy can be a little bit more difficult. And we learned two techniques for that. I'll give them their intuitive names, which is greedy stays ahead. Greedy stays ahead, which is essentially just recursion, or not recursion, induction, sorry. It is essentially just induction, where we're saying every time I make my decision, I am in the optimal subproblem. I have the best options ahead of me, and I will be ahead of any option that didn't make the decision I made. But essentially just induction. The other option is exchange, which I said is essentially counterexample, which is maybe a bit of an overstatement. They have a relationship that's a little bit difficult to see intuitively, but the idea of exchange is basically we want to turn some arbitrary optimal solution to our problem into our solution. And we can do this through steps. So we can say in an inoptimal solution, let's say that we have some arbitrary optimal solution to this problem that is not the same as ours, that is not just taking the top most valuable ones, and then we'll say okay, instead of taking V1 and V2, it takes V2 first and then V1 and then so on. And what we say is that in each one of these we can exchange one decision that we made. So instead of making the decision to take V2, we will instead take V1. Right, so we'll exchange these two, and what we'll notice is we choose some exchange such that we are closer to our algorithm. Here in this case, I'm saying that this is ours, and this is defined as the optimal solution, or an optimal solution. And what we see is that every time we exchange, our solution will either stay the same in terms of its quality or get better. And by doing that, in this case, there will be some threshold. So exchange, this is the total amount of paintings we can take. In this case, the solution stays the same. If I swap these, then the total value remains the same, but that's okay. So I can just say that every one of these exchanges either keeps the metric that I'm trying to maximize the same or increases it. And by doing that, then I can say that I can iteratively do that until I turn this optimal solution into my solution. And if I turn it into my solution and the score, the metric that I'm trying to do, has only gotten better or stayed the same, then my solution must also be optimal. Okay? Does that argument make sense? Raise your hand if it makes total sense. Okay? Raise your hand if it makes some sense. And raise your hand if it makes little sense. Not very much sense. Okay, cool. Yeah.
Just a question on, technically you don't have to exchange from an optimal solution, right? If you show that if you exchange from any solution to our solution, it gets better.
So the argument that you're saying here is it's not a singular other solution, it would have to be any solution. So you'd have to show that for any arbitrary solution you can do this, and it's easier, it's strictly easier actually to do that with just an optimal solution. So by doing what you're doing, you implicitly have to do what I'm explaining. And this is just a slightly easier thing. There are some problems, perhaps, where it'd be easier to formulate what you're saying, because we don't know the structure of an optimal solution always, but you will always have to prove this. This is the thing that gives us optimality. Yeah. Now, you can get it as a byproduct of showing that every solution does this, but most of the solutions won't be useful for the proof. Does that make sense?
But if you just say any solution can be transformed into our solution,
Yes.
you don't have to necessarily care about the fact that some of those are optimal
So the only ones that would give us the proof that ours is optimal are the optimal ones.
Okay, sorry.
Yeah. No, so I understand the confusion perhaps a little bit, but I am actually right on this one. I know sometimes you correct me, but I am right on this one. No, as long as we need to show that an optimal solution is less than or equal to our solution. That's the thing that we need to prove to show that we're optimal. Okay, so this is greedy. Greedy is relatively straightforward, sometimes very useful, generally not that helpful. For any like hard problems, we're not going to have a solution like this. Most of the time, if we have a problem that is important enough for us to be spending time making an algorithm for it, this is probably not going to be the approach, because then it wouldn't be an important problem, generally. That said, there are some interesting greedy problems, but they aren't particularly exciting. There's other ways to formulate them. Greedy does also have some interesting theory. It's difficult to see if a problem does have a greedy solution a lot of the time. And there is some interesting thing, the theory of matroids, which I mentioned, which you do not need to look up, but if you're curious, you can tell us whether or not there exists a greedy solution. There's also probably some researcher out there who is screaming if they heard me say that greedy is not important, so I'm sure there's something important with it, but not that I've found. Nothing that I've come across that's particularly compelling. That said, today we're going to be moving to the next topic, which is sort of compare and contrast with greedy here, which is dynamic programming. And it is uncontroversial for me to tell you all that dynamic programming is the most important subject you're going to learn in this class. We're going to spend the most time with it. We're going to sit on it for quite a while because, one, it is a concept that a lot of people have difficulty with. I'm going to try teaching it in a way that I think was intuitive. There's a lot of different ways to explain it. But dynamic programming is going to be close to state-of-the-art for a lot of solutions. And dynamic programming is also something that, at least historically, has been very heavily tested on coding interviews. It's what I got tested on my coding interviews that I took recently. So it's something that you should have in the bag, and it also is a very clever thing, and the underlying methodology is very useful. Okay, has anyone heard of dynamic programming before? Okay. Here, let me. Who wants to give a go at explaining what it is while I erase? Yeah, go for it. Okay, so you described it as identifying subproblems and then solving those subproblems. We'll see where this definition is lacking fairly shortly. Not to call you out, but there is an underlying, more interesting thing that's going on with dynamic programming. As an example, let's talk about Fibonacci number. You have a question? No. Okay, no, we got it. We're going to talk about Fibonacci numbers. Who knows Fibonacci numbers? Okay, basically everyone. In case anyone has missed them, here is how they are defined. We say that the nth Fibonacci number, oh, why did the marker suddenly die? The nth Fibonacci number is going to be equal to the previous Fibonacci number plus the previous Fibonacci number. Oh, minus 2. And we're also going to define it in this class. You can sort of define your starting point however you'd like. We'll say that f0 is equal to 0 and f1 is equal to 1. Okay? So then, what is f2? 1. And what is f3? 2. Cool. We're all good. We get Fibonacci numbers. Now, let's imagine writing an algorithm to calculate Fibonacci numbers. Okay? Let's say I give you some number n, and I ask you to find the nth Fibonacci number. Take a moment, take 2 minutes or something, try to think of an algorithm, write it out, and then we're going to talk about it. Okay? Go. If you already know an algorithm, think of a good algorithm. I promise you don't know the best one. Yeah, fine. Well, there's better ones still. Yeah.
Have a little peanut brain though.
What?
Just have a little peanut brain though.
A little peanut brain?
Yeah.
I'll come up with a bad one.
Okay.
Take it from him.
I don't. The explanation for it took. I get to like five malls a lot of your It still kind of blows my mind.
That's just like design an algorithm to find the answer. Think of a really bad algorithm for it. We'll talk about it in a second. Okay. So let's talk about it. Simple algorithm for this. Anyone have a fairly naive simple algorithm for calculating Fibonacci numbers? I already answered one of that. Sure, Amanda. I'm not going to call on you in case you use a spectral decomposition. Yeah. All right, cool. So this is a very natural way to approach this problem. We say, let's define our function. I'm grabbing a different color. We define our function. Where's the blue marker? You guys had it. Not that one. The other blue marker.
That was the one we were using.
Oh. Okay. Whatever. She was using it. Okay. So a very natural thing for us to do. Yeah, I don't know why that marker's not working well anymore. A natural thing to do is we can define our function fib, let's say, of n, and we can say if it's one of our base cases. This is a sort of solution that would come naturally from all the things we've talked about so far in class. We say if n is equal to 0, we return 0. If it's equal to 1, then we return 1. Otherwise, we're going to return fib n minus 1 plus fib, I just wrote f, it's fine, minus 2. Okay? You might have to deal with edge cases of what if n is negative. Well, we're not going to worry about that. We're going to say it's a good type of input. It's going to be an integer, a positive integer, whatever. You go through here. This works perfectly fine. This will, in fact, give you the nth Fibonacci number. What's the problem? Why am I not saying this is a great solution? End up recalculating a lot. In particular, how long do you think this would take to calculate the 100th Fibonacci number? Yeah. Yes. Very slow. I think 100th Fibonacci number on a fast computer would probably be about a week. It's a very, very bad. In particular, let's look at the runtime. This is where runtime analysis is going to be our friend. So what's the recursion look like? Sure.
2 to
So
times t to n minus, well, I guess n minus 1, t n minus 2
yeah.
plus c.
Tn minus 1 plus Tn minus 2 plus, what do you call it?
C.
Plus some constant time. It'll be we can just say constant time, that's fine. Okay, now, what does recursion give us as a full runtime? Can we bound this at all? Well, let's draw the recursion tree. Okay, so we have, first off, n. I think I'm gonna erase a little bit so I just have more space here. I'm gonna erase the definition of Fibonacci numbers. So we can start with our base, which is going to be n. It's going to do 2 recursive calls. N minus 1, n minus 2. Cool. And then it will recursively go again. What is this one right here? N minus 2. What's this one right here? N minus 3, and etc. This is going to be n minus 3. This is going to be n minus 4. And how much work is that at this level? It's going to be just 1. How about at this level? 2, 4, etc. How deep does this go? How about this? How deep is the shortest part of it? going to be n over 2. It's going to be this branch right here is only going to go n over 2. And this branch over here, the longest branch, is going to go to n. It's going to be n times, right, eventually. I'm not going to worry about it too much. It's going to go n. So at this layer, how much work is done? So it's going to be 2 to the power of n over 2. Okay? Cool. And then how about at the nth? 2 to the power n. Cool. But there's going to be some missing here. So we know our runtime is going to be somewhere between these two numbers, right? And if we talk about asymptotes, what can we say about this? Yeah, so we can definitely say that this is going to be upper bounded by 2 to the n. And we can also say that it's going to be lower bounded by 2 to the n over 2. All right? Cool. Secret sauce of this is that these are going to be equivalent. So this is going to also be, so we can say that 2 to the n is actually going to be upper bounded by 2 to the n over 2. Would anyone like to explain why? Yeah. Yeah. So this division here is just going to be a constant division, right? So this is going to end up being, so it's maybe not tremendously obvious, but these two are essentially just going to be the same order. Both of these are ordered 2 to the n. This extra constant factor won't actually matter for us. Okay. So this whole thing is going to be 2 to the n, and 2 to the n is very slow. 2 to the 100 is order of atoms in the universe times 2 to the 40. It's very, very big number. So just calculating a relatively small Fibonacci number, we are met with a horrible, horrible runtime that makes it infeasible to run this. If you code this up, I recommend you do it. Just code this up. It seems like an obvious, intuitive solution. This will not be able to run. You won't actually be able to use it. Even on relatively small numbers. I think the cutoff for being able to get a relatively fast solution like in the same day is something like 20. It's a small number. So what do we notice that could maybe help us out? So this seems like a lot of computation to be doing, 2 to the n. Right? This is order 2 to the n. Right? So what might we want to do? Someone, I think Ezra, you said some comment here. Can you point out what's happening? So when we're doing this, when we're running this code, we are calculating Fibonacci number at n, then we're calculating the Fibonacci number at n minus 1 and n minus 2, and then we're calculating it at n minus 2 again, n minus 3, then n minus 3 again, etc., 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 etc. So what happens with code like this is that we keep repeating the same computation. If I were to draw the tree out from here, you'll notice the tree from here is exactly the same as the tree from here, right? So this ends up being n minus 3, n minus 4, and if I continued through them, they're going to be exactly the same. Same for this one. This is going to be the same tree as this one as I go through, and this one, in fact, will be the same one as that. And we end up with a lot of repeated computation. So the fundamental idea of what we're going to be doing with dynamic programming is we want to not repeat that computation. So this is, if I needed to give you a single sentence as to what we're doing with dynamic programming, it is we never recompute something we've already computed. Okay? If you want a single sentence for the point of that, that's what we do. So, anyone have any ideas of how we could go about changing this so we don't repeat this computation? I'm going to give you a couple minutes, actually. Talk in your groups, see if you can do it. If you already know a way to do it, write a proper algorithm. Give me a couple minutes to think about it.
What is it? Just like I think it's actually more intuitive. This is your first time teaching our session.
I prefer to teach in data analysis, but I just cut you off because I don't write everything up. It has happened to me. You will catch me occasionally, but I swear I guess. You know what the almost solved, by the way? It's the most embarrassing term in all computer science. Maybe the second one. Well, I'll say it in a second. I'm going to say it a few times in the computer. That's not the word though. It has a specific word. If you look up caching for dynamic programming, there's a specific word. And it's really funny. It made me laugh a lot as a student, but now that I have to say it in front of the whole class. And you'll see, you'll hear it in a minute. Okay. Anyone got any ideas? How can we speed this up? Fine, you can go.
You like make an array and you start from the 0 and 1, so you don't recompute.
Yeah. So this is one of the other core ideas of dynamic programming. And the way that we are going to not repeat our work is we're going to save our work. So in particular for this solution, what we can do is we can create an array where we have, first we're going to store in the 0th and 1st index the 0th and 1st Fibonacci numbers. And then we're going to change our base case to instead of it being this, just those two, we're going to say if, we can say that the rest of them are just like none or whatever if we want to make it proper code. We say all these are none. And we say if, and we'll call this whole array F just to give it a name. Sometimes in dynamic programming, by the way, the notation is to call this array opt because it is the optimal solution for each one of these. In this case, it doesn't make sense to call it opt because I'm just calculating Fibonacci numbers, but you may see that in some literature if you look it up. Anyway, so we say if fn is not none, I'm going to give it some Python notation, is not none, then we're just going to return fn. Cool? Otherwise, we are going to say that fn is equal to fn minus 1 plus fn minus 2, and then we will return fn. So this is assigning it in the array, by the way, if it's not clear. Okay? So let's look at a little bit of computation. Let's say that we have fn 5. Okay? Let's say we're making that call. All right? This is a global array, by the way. This is usable by any call. So if we did something, let's do fib4 instead, just so it's pretty easy. So I can say fib4, okay? And it's going to make some recursive calls, right? So it'll go to this line, and it'll make it the recursive calls. It'll do, I guess, it'll have to be fib, sorry. So this has to be fib, just to make sure that it's very clear. This is going to be fib n minus 1 plus fib n minus 2. If they're already filled in, then it will just return the indexing from the array, but if they're not, it has to recalculate them. Okay, so then it'll do the first recursive call first, so the fib n minus 1, so it'll do fib3, and then fib3 is going to make another recursive call, and it'll get fib2 and fib1, 2 and fib1, 1. And then here, it's going to have a recursive call that is just going to be fib1 and fib, I'll write them out actually, fib1 and fib n minus 1, or fib0, sorry, fib0. Fib0, but these are both cached, so we're going to then just pull the cache value for both of these, then we're going to store this one in cache. This one is also from the cache, then this one, we can just use the cache versions here. There we go, and then when we go to the other side to make the call, do fib2 here, it's already cached. We already have it in the array, done. Now, question for you, hopefully this made sense. Essentially, we're going to only be filling it in from this way forward. Like, we're going to fill it in from the lowest values to the highest values, starting from whatever our base cases are. Now, question for you as a lot, and I want everyone to come up with an answer to this, by the way. I don't want someone to just shout it out. What is the runtime of this? Remember, the runtime of this was 2 to the n, which is astronomically high, you know, heat death of the universe to calculate fib50 type situation. So, what is this one, do you think? I want everyone to think for a second. I want everyone to get the answer, if they can. Yeah, you can discuss with a neighbor. Give it a little bit more time.
So it's n minus 1.
It's not actually that. I typed it up.
I was gonna say,
But
that's
it's just,
like,
it's
oh,
just
wait,
one
no.
thing that I always use for my for now I have to.
No, it just sounds like you're a French saying.
Yeah, no, but I think it's more like a list. The word that describes it.
Yeah, okay, that makes sense.
If you don't respond to text for a while, people will.
I don't think I died.
All right, I want to hear some suggestions. What do you think the runtime is? Sure. O of n. Let's put the suggestions on here. Anyone think anything different? Any other suggestions? That's a pretty big jump of 2 to the n down to O of n. Anything in between, maybe? Absolutely no other suggestions? Okay, who is confident that it's O of n? Okay. Well, good on you, it is. So in fact, the runtime of this is O of n. The easiest way to see this is essentially that we're only going to be filling in each one of these one time, right? And this array is going to be n long. Eventually, the last term here is going to be fn. We'll define our array that way. And we're only going to fill these in each time. And if I count the number of times that I do a cache call, it's going to only be some order of n. It's not going to be exactly n, by the way, so you can maybe do the counting there, but it's going to be a constant multiple of n. Okay? Yeah. So that's what I'm saying. I'm saying the number of calls to the array of index of calling an element from the array, which we say is constant time, by the way, which is sometimes not a good assumption, but we can say that here. That we're going to say is there's only n of them. There's more than n, but fewer than something greater than order n. So it's going to be order n. Cool. It's in fact going to be theta n. It's going to be exactly n. Exactly bounded by n. Tightly bounded by n, I should say. So this is a very dramatic speed up, going from 2 to the n down to order n, and all we had to do is we had to save an array. Now, this idea of taking our things that we computed and memorizing them in an array has a specific name, which I think is the second dumbest name in computer science, which is memoization, which is essentially just memorization, but said with a lisp. Memoization. So we can, I'll write that here. It's a term that maybe will make it more memorable for you. Memoization. Genuinely, I'm not kidding. That's a term. So memoization is the concept of memorizing. I don't know why they just call it memorization. Of memorizing all of the things that you've previously computed, and a lot of our job is actually going to be deciding what is needed to be saved and what isn't needed to be saved. By the way, that's a big thing here, and that can give us a significant boost to our runtime. This is essentially you've probably heard at some class the trade-off between storage and like memory and runtime. This is the most clear example of this. By using some of our memory, we're able to speed up our algorithm dramatically. Do you have a comment?
You said this is the second.
I forget their names, but there are two professors who have the last names Cox and the last names Zucker, and they invented a machine which they then dubbed the Cox-Zucker machine. You can look it up. Actually, genuinely real. I'm not kidding you. Anyway. There are some fun things in computer science. So, what is the asymptotic memory complexity of this algorithm? Now we're going to start worrying about this at this point in the class. Worrying about how much memory we're using. So how much memory are we using? Sure. Order n. We're going to assume they're integers and all of this, so we don't need to worry about like how much space each one of them takes up in memory. We'll just say they're small enough integers. Let's not worry about it. We'll have an n-long array, and we'll say that that's fine. There's some nitty-gritty there of if I had very large integers, I can't store them in the same amount of space, but we're going to not touch that for now. We'll maybe talk about that later when we're being more specific about our memory usage. So order n. Who thinks that is as good as we can do to still get order n runtime? Okay, raise your hand if you think that this is as good as we can do. Yeah, why would I be talking about it if it wasn't? I get it. I appreciate the bravery of saying it is. That's reasonable. It's reasonable. So what could we do? Yeah, here. Exactly. We only need the previous 2 Fibonacci numbers to calculate any Fibonacci number. So in fact, instead of having this entire array, we could just save 2 numbers at a time. So if we just save 2 numbers at a time and only reference those 2, then we'll never end up with this repetition. We need to be careful about how we do it, though, because the naive way of doing it, if I just ran this algorithm the way I've described it, you'll notice by the time I finish this whole chain, I end up needing fib2 again, right? So this naive implementation of just do this but memorize would not work, right? So we in fact need to redesign our algorithm, and the way that we're going to end up doing that is another concept in dynamic programming is we can essentially do this as a okay, I'll just write it first and then we can talk about it. We can do a for loop. We just go through, so instead of doing this as a recursive call, I know we love our recursion and all that, but instead we can just linearize it in a way. So we can say for I in range n, let's say, range n, we're just going to say that we'll start with sorry, I'll say we'll start with previous equals 1 and previous, terrible naming convention, equals 0. And then we're just going to say for I in range, I'll say n minus 2, because this because we already have 2 filled in. Then we can say that we can just add them together. So this is going to be, I can be slightly more efficient about this, but I'm not going to worry about it. It's going to be previous, I'll say current actually to keep with my convention. So current is equal to previous plus previous plus p squared, previous. And then I can say after this that previous is equal to previous. Sorry, this is I'm dealing with the consequences of my own naming scheme. And then that previous, that previous equals current. Okay. Then do this. This is just swapping variables around, and then at the very end, I can just return either current or previous are going to have the same values. So I'll just say previous, so I can say previous a couple more times. Previous. Okay. So all this does is goes through. It just has 2 values really plus current. All right, and this will originally take the values of f0 and f1, right? And then I'm going to iteratively calculate some new f2. Some new other one, and I'm going to reassign them like so, and I can just iteratively do that. So I only use, at any time, 3 variables. That make sense? So in fact, we can do Fibonacci numbers in theta n time and O1 memory. Okay? So that's very good. That's very good. As a little thing that if you're curious, you can look it up. We, in fact, can get lower than this. There's a fun little thing for you, is we, in fact, can turn this into theta log n, and O of, depends how you calculate it, but we can essentially say O of 1. There's details there that I'm not going to talk to you guys about in class. But I'll say O of 1, that's fine. Yeah? There is a way to formulate it as matrices, and there's a way to formulate it just as a, so here, I'll give you this just so you can see that this is a sort of like, when you get to very optimized algorithms, you end up with some weird stuff. The very optimized algorithm for Fibonacci numbers is this. Fib n equals the ceiling of 1 plus square root of 5 over 2 to the power n. Awesome. It is beautiful and elegant, the fact that we can do that. It's log n, by the way, because exponentiation like this is log n. Yeah. There is a way to treat it as matrices, and that's how we derive this answer. But okay, this is like the end game. This is like when you're super optimizing your algorithms, you sometimes will end up with stuff like this. But the first step towards that is dynamic programming. So dynamic programming is our first step into the realm of optimized algorithms, where we can start to see the trade-off between memory and time. Yeah, yes? Are you going to turn around and walk out if there isn't? No. Okay, sit down then. All right, fine. Quiz time. Thank you. Yeah, there is a quiz now. Yeah, so I'm going to have you do. Yeah, question first. Yeah.
So the iterative method is the like memory storage.
What?
So like the iterative method.
Yes. So the difference between doing our original method, where we just did some memoization, and doing this iterative method, is that we saved on memory. Generally, we are co-optimizing runtime and memory. Sometimes we're able to do both at the same time. Sometimes there's a trade-off. And the trade-off is actually a very interesting theoretical results about that trade-off. We'll see problems where we have to make that trade-off, actually. But one thing that you might notice about it is generally the runtime is going to be upper bounded by the memory usage, is a thing that you can think about. Yeah. Okay, so this quiz is going to have you work on a dynamic programming problem. I'm going to give you perhaps a little bit more time on this one, just so that you have, it's written essentially like a test question. I think we'll probably do 15 minutes total on this one. This would be a pretty classic problem to ask in like a coding interview. So you can give it some thought. Oh, one more thing, by the way. I don't know if this is public or not, but someone made a post on Piazza asking me to crack down on people not in the classroom for the quiz. I know, and that would be ridiculous to do after getting so much backlash on the other things. So I'm going to do it, so submit it before class is over. Okay, I'll remind you right at the end of class, but submit it. The due date is going to be like 6 o'clock or something, just so that people have to do it in class. For bonuses, you can submit it later. Yeah, I got you. Yeah. Okay, go. Continue.
That's so cringe. It's like a student said that.
I also think we're pretty decent at that kind of stuff. I'm not actually worried about it, but I'll do it pretty fast. Oh, you didn't get into one. Anyone else still need the quiz? All right, I'll grab them in a second. Yeah. So this is a variant on the problem we talked about on Monday, by the way.
Like they have like multiple copies of them. So
It doesn't matter. You can have multiple copies that have the same text.
but it makes it a little more difficult if you have to consider the practice.
You guys can actually give you a reduction. Yeah. Why wouldn't you? You have happens when you get a little confident.
Yes, it is.
All right, real quick, I'm going to check in. Anyone come up with any heuristic? Any greedy solution? Yeah? Okay.
I don't want to shoot. Does that mean it's bad?
That doesn't necessarily. All right, how about, okay, one of you two, because both of you, I think, thought of it. Yeah.
A weight to value ratio.
So what if we had some max weight. What if we just take the highest ratio of value to weight? So we create each one of these, right, for each one of them, and then we just sort them by that, and then we take the highest one, and we continue down to the lowest one. Do we think that's going to work? Why not? Yeah.
Well, you can have like a
Yeah, so let's do a specific counterexample. Specific counterexample would be I have two items, let's say, two possible items. I'll say it as 3 items. I'm allowing you to take the same item multiple times in this, but I'm just going to have 2 items be duplicated to be obvious. So I'd have one that has some particular value, let's say x, and it has a weight of max weight over 2 plus 1. Okay? So I have a ratio of that over that, right? Then I can have 2 other items, which are just going to be x over 2 plus epsilon, and then w over 2, exactly half the weight here, right? I can choose my epsilon such that this has a higher ratio than this, by the way, in case you're wondering about that. Cool, cool. So then if I have 2 of this, right, then I could take both of these, and I would have x over 2 plus, or I'd have x plus epsilon, or 2 epsilon in this case, value from choosing these twice, versus this one where I would only have x. Does that make sense? So clearly I've gotten more. I could come up with a less narrow example, like this is just barely winning. You can come up with much clearer examples of one winning over the other. But the basic idea is that taking this, very similar to the scheduling, taking this one will block off the option of taking 2 of these ones. So I can end up with a whole bunch of excess weight that I can't use anymore. So in fact, using the highest ratio from value to weight does not work. Okay? That makes sense? Yeah. You take the same item multiple times, it's fine. We can also just assume that there are duplicates, duplicated items that have the same value and weight. So it's the same problem. Yeah. And I will tell you, in fact, this problem is not solvable by any greedy algorithm. It is not a matroid. What I'm testing you on today is dynamic programming. So today, you need a dynamic programming type solution for this problem. And with that, I will open it up to you talking to your neighbors. All right? Keep working on it.
Put the items in a dictionary, the value and the weight, and then while the person's weight is greater than 0, you get the max VI in the dictionary, and the weight would still be greater than or equal to 0. You append it to the set of things they can carry. You subtract that from the weight, and then swap that item from the possible items. And then if you find the highest one of the weights too high, you go and find the highest value of the weight less than I'm just starting with the highest value and then I just keep it over and over again. Every time I add something, I pop it from the possible. Okay, what did you or like No, I see what you're saying. It's all those weird little like random combinations. Oh yeah. This is kind of like a problem that we did in a discussion where it's like you have an array and you need to find the greatest like continuous if there's no middle part. Do you go to the discussion? No, I have no idea. This is like a discussion we did, kind of where there was like an array, but like there could have been that weird middle part that was better, but we didn't know. It does. And he knows how to do it too. So what was the problem on the exam that you lost?
The actual answer
Is your algebra class the greatest from this? Oh.
All right. Hint time. I'm gonna let you guys keep working on this because this is a famous canonical problem that if you just read in a textbook, you'll be like, oh, it's obvious what we could do. But I'm gonna let you struggle on it so you can appreciate it. First thing first, the naive solution of just trying every possible combination would give you. Anyone know the runtime of that? What it would take? Every possible combination? Yeah. It would be O to the n actually. So it depends. If you allow duplicates, then it could be n factorial. If you're not allowing duplicates, then it would be O to the n. Whatever the case, it's ridiculously high. What we can get is, anyone want to give a guess? Yeah. Oh yeah. Oh yeah. Sorry. Yeah, don't shout it out. All right. Oh my god. I do have the blue one still. It's okay. I got it. It's going to be O of n. So we can in fact do the O of n, and the array that it makes the most sense to memoize is going to be an array. We can call it opt if we'd like to, which is based on the weights. Okay. So this element here would tell me the optimal value. I'll write it all the way up. Optimal value for max weight 1. Okay, that's your hint. Continue.
So the array is as big as how many as like the highest weight.
Well, okay, so this is the sign. We've already seen that in the same way. We check
So would it still be naive to look at like every combination of those things that equal the weight and then find out?
Regardless, you come up with a pretty solution. Like, don't make that you have a chance but it's hard for me to parse it out. Oh, that, yes. Is a famous dynamic programming problem. This is the knapsack problem. This is the real knapsack problem. The other one was the easy knapsack problem. So the max weight total. So, yes. So the optimal amount of value I could get if one actually worked of like what's the best thing to do.
But then what if like the weight time and then weight time had to work the most.
Yeah, no, that's good. But this is like, we're still gonna have like search to get a lot of possibilities.
Basically, you don't want to look at every single combination.
Yeah, exactly. Of like looking through every combination, because instead of looking at every combination that moves fast, every combination
You compare those to
like to save the result of like, oh, what can we do the rest of the space? You don't have to.
okay, that makes sense. Like it's just each side.
Something one and then has a result.
And then set it to 0.
I have to highlight.
Just rescan, right? Yeah, I guess normally there wasn't. Yeah, no, so you're talking about 0, 1, which is a different variant. But they are equivalently different.
So the last element.
And regular knapsack doesn't have any.
Or the highest.
I should be
The lesser result if one there exists an item lighter.
All right. Who would like the solution versus who would want to solve it on their own? So who wants a solution? Okay, majority of the class. I think I will go through an outline of the solution. I'm not going to do it fully properly. The rest of you, I guess, cover your ears. I don't know. And then, by the way, this is the knapsack problem. So previously I called the other problem the knapsack problem. That is the easy version of the knapsack problem, or what we will, if you want to look it up, it's called fractional knapsack. It's equivalent to that problem. This one is the true canonical knapsack problem. We are even in the canonical one, we're a thief with a knapsack full of stuff, even. This is totally the original thing. On Friday, by the way, you're going to get another crack at this, so maybe listen up to see. So the idea of what we're going to do is we're going to say, when I have a max weight of 1, if I were to have max weight of 1, then what would be the optimal value I could get, hypothetically? Yeah. Exactly, the highest value thing that has a weight of 1. So I can just do a maximization over all the possible options here, and I'd get some value. Let's just call this, let's say it's 5, sure. Then if I were to try to fill in the next spot here, if I want to know the max, what is the max value I could get when I have max weight equals to 2? Well, there's 2 options for us. Either we can just take an item of weight 2, or we take a combination of things. But what would be the max out of the combinations that I could take? It would be 2 of the optimal choice for 1 weight, right? So, because of that, I would say that this is just a maximization between the max that has weight 2 and 2 times this. Okay? Yes? Yes? Yeah? Yeah, I said allow duplicates. Yeah. So we're allowing duplicates. You can think of the version that doesn't allow duplicates. It's called 0-1 knapsack. If you'd like to look that up, it is slightly different, but is a strictly easier problem actually. They're equivalently difficult, but it's like you can prove that it is easier. Yeah.
So this duplicates you meant.
Yes, you can have as many duplicates as you'd like.
Oh, I assume it's just there can.
If you don't assume that they're duplicates, then it does make the problem slightly easier, actually. But I digress. It makes it slightly harder to code, perhaps, or slightly harder to write out as an algorithm, but it makes the problem itself easier. Anyway, continuing. So here I can just choose between all the things that are max weight 2, and then I can choose between that and 2 times this, right? So then I can just do a maximization between those things. And what I'm going to say is that, okay, I'm gonna give you a hint because this is going to be your Friday problem. I want you to think about this. Maybe look up the knapsack problem if you'd like. Work on this problem on your own. If you'd like more time to submit the quiz, I guess I can extend the deadline because I don't really care that much. But I'm going to leave the lion's share of this to you, but I'm going to give you another like key insight that we can make here. So it may be like you may think that at some point, let's say that we're looking at n here, like we're deep into it now. You may think that when I want to find this, I can maximize over all of the things that are size n. Then I would need every possible combination of things that sum up to n from here, right? But it turns out that it is sufficient for me to just look at all combinations, all pairs that add up to n. And this is a little bit of a tricky thing to prove, but it turns out that by doing that, I'm only ever going to need to do n different checks here. Okay? N is maybe an inappropriate number because I used n earlier. Let's make this some like k, whatever. So I'd only need to do every possible pairing between things. Anyone have any insight as to why I only need the pairs? I don't need to do every single combination? Sure, give it a shot. Exactly. So you can think if I were to look at, if I were to look at the number 3, right? Then I can do it as a 2 and a 1, or I could do it as a 1 and a 1 and a 1, right? But when I chose the max weight for 2, I already considered the option of a pairing of them together, right? So it doesn't matter if I know like what exact items I choose, I just need to know what the value is. So by just looking at the pairings, I'm looking at every possible combination actually, which is a clever insight of this problem, and that's how we can get the runtime down so low. If you didn't quite understand that, which I think it was a little bit of a fast explanation of this insight, that's okay. You can re-listen to it if you'd like to. Or you can look up the knapsack problem. So on Friday, we're going to do another dynamic programming problem that is very similar to this, but not exactly the same. If you'd like to look up the solution to knapsack as practice, it's